So this is heat system design, week 4, and part 1. And we're talking about energy and building shell. So you'll hear these terminologies a lot if you work with something like mass save or greenhouses or mass clean organizations. When they're trying to conserve energy, we'll hear about building shell. What is that? What does that mean? Let's treat the building as a whole envelope by itself. So we'll talk about the building shell, building construction, basis of transmission losses, and windows and doors. So this question is you're gonna ask this a lot, at least 3-4 times in this year and next year. It's in a house, how do we lose heat or gain heat? There are 2 means of heat loss in a house. It's not convection, that's heat transfer. Heat loss is for heat gain, basically 2 things. One is transmission. That's going to be conduction, and radiation. That's transmission. We're transferring heat through material. We're losing and gaining heat. That's transmission. The second way we lose heat in a house is what? Can somebody guess? Naturally? No? What else?
Air leakage?
Yes, it's called
Infiltration?
infiltration.
What's that? Oh,
Air leakage. So either we lose heat through the walls or air. Cold air comes in, it cools our house instead we want to be hot, or we lose cold air to the outside. Yeah.
We talked about transmission of heat, so this is stove, that's would be convection, right?
Yeah.
Could be a gas stove, right?
Yeah. When I'm thinking about heat loss, I'm thinking about the house as a box.
Right, yeah.
So this box losing heat through the walls, the windows, that's transmission.
But it's the same thing though, too, because even convection,
Guys.
in a gas stove, you lose heat loss when the
Yeah, but that's convection. That's the air.
Okay.
Wait, so what is convection and what is convection?
So we talked about that last week. I would say conduction is heat loss through solids. Convection is heat loss, heat transfer through liquids and gases, fluids, and radiation, waves. Fluids can be liquid or gases. Waves. I would say there are 2 types of convection.
Yeah, free and forced.
Forced and free. Forced if you have a pump or a fan. So transmission through the walls and windows. Windows and doors, they both have transmission through the panel, also have a lot of air leakage. So these areas leak a lot of air. That's why we put molds with a stripping. So transmission and infiltration. So this fenestration is a fancy word for doors and windows. So when they talk about the house fenestration, that's the windows and doors. So Doors are less common concerns of windows when it comes to infiltration. Why?
They're thicker and there's less glass.
Less glass,
They're better insulated than windows?
that's better insulated because they're solid. You can put foam inside. They don't have a lot of mechanical linkages. It's only, it will close shut. Windows have a lot of ways where you can open and close a window frequently. A lot of mechanism, fancy mechanism that can cause some leakage. Okay, so let's look at this graph here. So heat removed by the cooling system, this is in the summertime. So I'm trying to move heat outside, but heat is coming back to the house. How is it coming back? Solar heat to the glass panels, also heating the wall, that's solar heat. Air leakage and ventilation, you have to vent the way around it. Air leakage is to the cracks in the house, walls, and also internal heat. Where is internal heat coming from? Stoves, appliances, what else?
Yourself?
Yourself. Each one of us now is a 70-watt light bulb. So if I don't have the AC on, probably we're gonna generate a lot more and more heat. That's why big conference rooms and big halls, they don't require a lot of heat. Once it's full, it's gonna be so hot. That's why when you go in a concert, everybody is actually generating a lot of heat. It's the equivalent of 70-watt light bulb. You can see the light bulb. It's a lot of heat. So we have producing heat. That's internal heat, and also we have transmission from the walls. The walls get eventually hot. They get hit by the sun during the day. They get hot. The outside get hot. It will transmit through the wall, insulation if there is any, or even the air cavity inside. And eventually, if you touch the wall, it will feel a little bit warm to you. If it feels warm in the summertime, you need to have better insulation. Yeah.
Wattage, does the person generate per person?
It's an average depending on your size, but it's around 70-watt light bulb.
Okay, light bulb.
Yeah. It's at 1 feet. So 70 watts will be coming out of you the whole time. Heat. Let's go back. In the winter time, it's the same thing. The system is supplying heat. You're trying to heat the house, but you're losing stuff. You have air leakage, losing heat by air leakage, and heat losses through the ceiling. Usually you lose a lot of heat through the ceiling. That's why you also lose a lot of heat in the winter from your head. There's a lot of blood going on. So sometimes if you wear a very warm hat, probably very warm. So hat is very important in the winter. That's why you get this big, very Russian hats that use your head.
I have one of those.
Yeah, it's very, very warm. It's amazing how much if you cover your head, you feel warmer. So you lose a lot from your head. I think it has to do with the wind too. So it's a lot of ceiling transmission in the house. It's the same thing. You lose a lot from the ceiling because all the heat goes up. And also wall fenestration transmission. Same thing. You can transmit heat through the wall, lose some heat. You also transmit heat through the floor. It's not insulated. And air leakage and ventilation. So we have to always think about these things when we do heat loss and heat gain. And over the time, it could be a lot of losses. And it costs you a lot of money to heat the house and maintain the house at the correct temperature. So insulation and heat transmission. So let's look at this empty wall cavity. So you have two modes of heat transfer. You have radiation coming from one side. Let's assume this is the hot side. It's radiating to the other side through the air. Correct? And we said at any given time, every hot body emits a lot of heat in three ways: conduction, convection, and radiation. Everything that's hot will use three modes of heat transfer. So currently I'm radiating. That's why if I bring the infrared gun and 127 to measure temperature, I will bring my infrared camera and show you how it works, how you can measure heat. And so this is radiation. And I also have air inside. So the air will keep moving. Air is a good insulator if you can keep it still, but it's always moving. So, so air is always moving. It's gonna carry heat, cools off and come back. So it's going to be always moving. That's why when you look for a good thermos, inside, what's inside? Two walls.
Vacuum.
Vacuum, because there is no air. How come windows are not vacuum? Double pane windows.
Because you want them.
They fill them with argon gas. Sometimes they fill them with CO2.
Oh, yeah.
How come they're not vacuum? Yeah. Vacuum pressure is very high. It's 15 psi, and we have a lot of surface area. So if you vacuum that, you got to keep the glass under tension, and it will break or crack quickly. And if it cracks, air will go in, and then you lose the whole concept. You're gonna have the same idea here if we're going back and forth. This is solid wall. So we said the fastest way is conduction. Conduction is faster than convection and radiation. So we're gonna have conduction through solids. So this is going to, again, even though it's insulation, it's if this is insulation, you're gonna have conduction through it. If it's solid wood, it's going to be more conduction. But it's better to have insulation than to have an empty cavity. So depending on the insulation here, you can transmit more air. And if you fill the wall, you're gonna eliminate radiation and then reduce convection as well. So what do you notice about some insulation? So this is insulation. Why is this shiny?
So reflect radiation.
So this is for radiation. So any reflective surface will help in radiation. All right. Any questions so far? Transmission? Yeah.
So the radiation is going to cause the insulation to conduct. Is that how I understand it?
No. This is the comparison between an empty wall and an insulated wall. So if I fill the wall with insulation, I have reduced radiation and conduction. The only thing I have here is conduction, mainly. Again, there's always going to be three of them. But mainly it's going to be conduction, and if I have the insulation properly, I will resist heat transfer through the wall. Okay. So thinking of what a good thermos do. If you buy a good thermos like Stanley or Yeti or something, what happens? They have always foam insulation. There's a vacuum sometimes with the heat transfer, and it always has a reflective surface. You look inside, it's very shiny because it will reflect the heat. And once the vacuum goes out, the thermos is no good. So the bottom usually have big, thick foam for conduction because it's where you're going to set it, the cold surface. And around the water container, there's always vacuum. And inside the vacuum, there's also heat, reflective surface. And that helps out a lot. Okay, before I go with this equation here, I don't want to confuse you. So we said that before, I said heat transfer through a surface. It's a function of what? Let's say I have this door, and I want to calculate the heat transfer from inside to outside. What do you think this has to do with the door?
Temperature.
First of all, what is the temperature inside and outside? So that's going to be temperature difference. So if it's the same temperature, will there be any heat transfer?
No.
No. Okay. Good. What else?
R value.
The material, right? Resistance. And finally, area. How big is the door? Small door, small heat loss, big door, big heat loss. No area. Surface area. Any question about that? Does it make sense?
So it's area times resistance times material.
Yeah. This is the wall. How is the empty wall? Of course, the material make a difference. How big the wall, the door makes a difference, and also what is the temperature inside and outside. So if any of those things goes to zero, it's going to be zero. If temperature difference is zero, there's no heat transfer. The smaller the area, the smaller the heat transfer. The bigger the resistance, I mean the material, it will correlate to the heat transfer as well. So if I want to put this in number, it's going to be delta T, and the resistance is 1 over the resistance, because the greater the resistance, the less heat transfer I have. Make sense?
Why is it the inverse of
Because
material resistance?
the bigger the material, I mean the resistance,
Oh.
the less heat transfer
So you
I have.
want
So it's going to be
a
that.
smaller number. Okay.
Which is logical. More resistance, less heat transfer. So if I increase the resistance, I will decrease the heat transfer. That's the balance. Okay, and A is going to be A, and heat transfer we'll just call it Q. Or we can say HD, or whatever you want to call it, W, as long as you know it's heat transfer. So heat transfer through any area is, any wall area, 1 over the resistance times delta T. To make things easier for us technicians, you might go and find something called U. Because people do not like to see 1 over R, it's confusing. So they just give you the U factor, which is 1 over R. If you look at your heat loss book, you look at the back, they give you the U factor. Nobody wants to look at reciprocals and inverse. So just the inverse. If you look, bless you. If you look at these forms, they give you the R value. And that's what you're going to use in there. And so if you look in your book, you'll see both. If you look at the back of the book, you should be getting the book by now, because next week I'm going to give you your project to start working on it once you finish this chapter.
Do you want us to bring it into class?
Yeah. Huh?
Do you want us to bring it into class?
You can keep it with you. So if you look here, at the end there are tables full of the U factors for every material, building material. If you look at the book here, single pane, clear glasses for glass and doors. What do they give you? The U factor. So walls, wood, at the end U factor. You take the U factor and you put it here. And this is the last 10 pages all about the U factor. This is how I find the U factor. How do you find the area? Where in the wall?
Height times width.
Measure it. Measuring tape. Well, how do you find the temperature inside and outside? Temperature difference. Inside is up to you. You can put whatever you want. What about the outside?
Highest or lowest.
Yeah. So you're gonna go in the book. They also give you list of big cities by state. Of course, this book is from the 60s. This thing has changed a lot, so you can look up. Springfield, for example, the coldest day of the year, they designed for 0,
That's it.
and the hottest day of the year, they'll say 95. So let's look here for Massachusetts. So you have Boston. This is the first number is the coldest day of the year. Greenfields Scholar -2. Springfield 0. Second number, you don't have to worry about now, but we'll discuss that later. So, going back, K here is the material. Don't write this down. Stick with the 1 over R or U. Makes things less confusing. K is basically thermal conductivity of the material. Don't worry about that for now. That's what you need to use. So I went through details to explain to you the material, which is the K factor. If you look up K, it's the thermal conductivity of the material, which has a lot to do with the thickness. Of course, makes sense, right? Because if I use one of those, it's going to be different R. If I put 2 of them, it's going to be more and more. And that has to do with the K factor, which is the material substance. But we're not going to use that. When you go and look at stuff, it will give you the R value right away. It's R4. So you know now what is this used for. So all you need is U or R. And what is U? It's 1 over R. Questions? Yeah.
It's always gonna be 1 over R.
Yeah. And the other way around. And again, the main reason they put it this way is because this looks nicer and easier to look at. Nobody wants to go 1 over R and all this kind of formulas. Okay. Again, if we want to think about heat transfer rate, so what is the unit going to be for heat transfer? It's going to be BTU hour foot square at degree Fahrenheit. If you think of BTU hour per foot square, that's the area, the degree Fahrenheit, and also BTU hour is going to be the material given for U factor. And if I look at this, hopefully they give me units, or maybe not. There are no units. Okay. Yeah, they're trying to do some units, which is okay. So this is the unit for heat transfer. Heat use energy per hour, foot square, Fahrenheit. You need to know that? Not necessarily, but at least you know it's a function of area, conductivity, temperature, and Q. So the heat transfer you get is going to be per hour. This is how much I'm going to lose every hour. So that's the heat transfer rate, which is Q. Question?
Is it on BTU an hour / foot squared, is that times Fahrenheit?
Yeah.
Yeah.
It's the same thing with the kilowatts,
Yeah.
same equation.
And
That's metric. That's imperial. For HVAC, usually we use BTU.
Is that supposed to be kilowatt hour?
Yeah.
Okay.
Actually, I think this is just kilowatt, because watt actually is joule per second. So
Oh,
it's
yeah,
percent.
okay.
Questions? Okay. Here's an example. Very simple. But it could be also tricky. I tell you, 8 out of 10 times, this is something you're gonna miss out. And where is it?
Is the answer 64?
So try to visualize a wall and think about that equation and what material am I going to use. If I have a wall with a window, think with me here.
That's a big window.
If I want to calculate the wall area, just the wall, not the window.
The wall, you're gonna do the area.
Yeah.
Then subtract the area of the window.
Length times width.
Then,
Minus 4 times 4.
yeah, minus the window.
So
So this is what people always mess up.
So
They,
minus 16.
yeah. So if I have 8 and 10, and this is 4 by 4, what I always get students messing up, Felipe, is what they do the 8 by 10 and that's it. Make sense, Benny? So I want the wall, I want the window, because they are not the same material. So if I want to accurately calculate the heat loss from the wall, I'm going to do the wall material by itself and the window by itself. So the wall area eight 10 times 8 minus 4. What do I get?
64.
64 foot square.
that's how you do it, right?
Yeah. So then I will go and find the heat loss for that wall. I have the area. I'm gonna go find out the U from the book and delta T, and I get the heat loss from the book, to the wall. Yeah.
Do we have to take into account that things are painted?
No, unless it's thermal paint. I don't think paint is that much insulator. Yeah.
I mean, I know in acoustics it is. I figured it might work
acoustic
that way.
does, yeah. I don't know if your heat transfer, I don't think that much. It's like what? Very, very thin.
The man who makes a paint that will stop that will, the loss of heat.
There
will
is,
be
but
a
it's-
rich man.
It is, but it's expensive. He is a rich man. He is a rich man. There is actually something called aerogel, which is a fabric, 1 millimeter thick, that has the insulation of really big R value.
Wow.
But it's around like $70 a yard. So yeah, you can do that in your house. So wall minus window. We're good? So the area of the wall is going to be the area of the material without the. So delta T, so now we find this is going to be my area. This is trying to find the delta T. If it's, we want the inside to be 70 degrees and the outside is 20. If it's 70 inside and 20 outside, what is the temperature difference?
50. And inside, outside.
So why do I say temperature difference and I don't try to subtract all the time? Because it could be the other way around. It's whatever the difference
You
between.
could do TH minus TL.
Yeah, you could do that.
Would be the easiest way to describe it, I think.
So that's going to be 70 minus 20, and I got 50 degrees. Fair? Makes sense? Which direction? Is it going to be inside or outside in?
The latter.
Yeah. Hot to cold, right?
Okay. So whatever's hot.
Heat moves from hot to cold. If you want to do the opposite, you gotta put some energy. Okay, so this is the delta T. Fantastic. So we got the delta T, we got the temperature. Now we need to know what is the R value. Easy way, complicated way. Let's do the easy way. Book. Or your Uncle Google. You can go Google the wall, or you can go look up the material, and this is how you find it. Let's not worry about that. This is basically telling you that it's a function of thickness, but let's pick a number from here.
Now this wall, is that 8 inches of insulation or from inside to outside?
So same wall has a thickness of 8 inches, so it's 8 inches thick. And this is going to be 1.6 per inch. So I'm going to multiply 1.6 per 8. That's the thickness of the wall.
Okay, so it's the inside
Yeah.
thickness. Okay.
What do you mean it's the thickness?
Well, because if it was 8 from outside to inside, you'd have to take into account sheetrock, wood,
no, it's the
all
complete
that
thing.
stuff, plywood. Yeah. Okay.
Wait, so what's that K then?
That's the material property, but you said we're not gonna worry about it. It could be confusing. But just to explain to you that the thermal property of a material has to do with thickness. The thicker we have, the more insulation there is. The thermal conductivity of materials is how fast they conduct electricity and also heat. Of course, aluminum is highly conductive, and air is not conductive. Long story short, thickness, and I got the U factor, which is 1/R, and I found my U factor here. I'm not going to calculate it, I'm just going to give it to you. What is the U factor? It is 0.25.
Wait, how do you calculate the resistance? How do you know? Oh, the resistance.
So the U factor is just giving. I don't want you to calculate that, I'll give it to you, and it's in the book. So now we got the area 64, but this is a different wall. So I have the area of 80, and I have the temperature as difference as 50. What is the heat loss per hour for that wall? You multiply the area. I'm gonna multiply for this example here. You multiply 0.25 times 50 times 80, and you get the heat loss. So if I do that here, for that specific wall, 80 times 0.25. What do you got?
1,000.
1,000, okay.
Is it true?
I'll check it now.
Sure.
No, I don't think so.
Yeah.
I found it. It is 1,000.
Yeah, it is.
Good. So, if you can remember one thing from this class, it's multiplication of those three numbers. You have the T temperature from inside outside. U value is you look up from the book or online.
It's not supposed to be 64?
So,
No, this is a different one.
Oh, okay, yeah. I see now.
500,000, it's just a number.
What you unit is BTU hour over that's gonna be BTU hour.
So the answer is BTU. That's how much BTU is in the wall.
Now, how much BTU is going to go? It's going through the wall.
1/3.
1/3. Now, see, 1/3 is 100,000.
Oh, okay. What's 1,000? 1,000 is a kind of
I don't think it's anything. It's 35,000. That's close.
thinking of something else.
So if you think about it, this wall is going to leak 1,000 BTU an hour. So in an entire day, it's going to be 24,000 BTU an hour from that wall only. So that's a really bad wall. What are you going to do about that? Yeah, that's the only thing you can do.
Is what?
Insulation. You know, add some insulation, and you can cut down that by a very huge percentage.
So what's it comfortable?
Huh?
What's it BTU?
What's a good BTU? You want for the room to be around like 2,000 BTU for the entire room. But usually the room will lose temperature from one wall only, the outside. Make sense? A room has 4 walls, unless 2 walls to the outside, only outside wall you will lose temperature. So 1,000 is a lot, unless it's from one wall, unless the entire room losing from 1,000. Yeah. So for an average an apartment of 3 bedrooms, you want something around 20 to 30 BTUs an hour. Yeah.
I thought I could save money by not running heat in some rooms I wasn't using, and it ended up turning some inside walls to outside walls because how cold it
Yeah,
got.
you could do that.
And it really, yeah, but it didn't really save me a lot.
Did or did not?
It didn't.
Yeah.
That's cool.
Okay, so I'll do another example on Wednesday. And by next week, should be ready to start doing some kind of heat loss for a house. By following this turn down. Whoa. Huh? I didn't look at the homework. Did I post the homework?
I was just gonna ask.
Yeah, probably it's the same material.